Welcome to this hybrid event arranged by the IET's Anglian Coastal Local Network, which represents members in North Essex, Norfolk and Suffolk. Welcome to those of you in the local audience here at the University of Suffolk Waterfront Building, and welcome to folks joining via Zoom from other parts of the UK and indeed globally. I'm delighted to welcome you all. I'm Kevin Foster, I'm chairman of the Anglian Coastal Local Network, and I'll be your host for this evening. So without further ado, I'm delighted to introduce our speakers, Ben Vick and Edward Rees from Scottish Power. Ben is an export cable manager with 14 years experience working within the offshore construction industry in both offshore wind and oil and gas. In 2014, Ben started his own consultancy working on various offshore wind and interconnect projects in Europe and Asia, specializing in technical specification for cable installation. His work included East Anglia 1, Greater Changhua, MOG2, and an Energy Island project off the Belgian coast. We've got Edward as well. I'm not sure if Edward's doing part of the presentation, but just in case, you are, I'll introduce you. Edward has worked in public consultation and community engagement roles for 20 years, both for client and contractor organisations. He's worked for various contractors during the delivery phase of projects, including Docklands, Light Railway Platform, and Crossrail. Edward previously worked as Community Engagement Officer for 3 years on East Anglia 1. So tonight, Ben's going to talk about connecting offshore wind farms. So Ben, over to you.
Thank you, Kevin. Good evening, everyone. Thanks for joining us in person and online. So as Kevin said, I am the package manager for Scottish Power on the A3 project. So I'm responsible for the delivery of the connection from the offshore substations to the onshore substations. So on the East Anglia 3 project, that involves about 37 kilometres of onshore cable and about 147 kilometres offshore cable, and that's the supply, design, supply and installation. So this evening, going to be really focusing on the installation part of the project. One, because it's got lots of big toys in it and lots of interesting things you can look at. Two, I'm not an electrical engineer, so I didn't want to sit here in front of you and talk about electrical design and cable design when it's not my specialist subject. And three, overall, I like playing with big toys, and that's why I'm showing you the installation phase of the project offshore. So what I also do a bit of training programs in my other job, and I've taken a lot of the content from that, so I've based it on a very sort of high level. We're not going into the bones of it, but please, at the end of the presentation, if you've got any questions or you want to stand with me afterwards and have a chat about something in more detail, then I'm perfectly happy to get into that. We'll be looking at submarine cables and the engineering behind it, installation analysis, so how you take a rigid copper structure, wound it round a big cotton reel on a boat and install it under the sea. How we develop a route in the cable routes offshore. So as I said, the East Anglia 3 project are about 147 kilometres of cable to be installed under the seabed. So how do you get that cable in there? How do you develop the route to make sure it's physically possible to install that cable there? We're looking at the route preparation, so how you have to prepare that route to enable the installation of the cable. We're looking at cable accessories, cable loadout, landfall, how you transition the cable from the sea to the land, cable ships, and also cable lay equipment. So a big broad range tonight, so hopefully it's of interest to some of you, or if not all of you. So why we're here, we're talking about submarine cables. So I think everyone's seen in the news, and the global demand for offshore wind is skyrocketing at the moment, but there's always a way. You've got all these beautiful big wind turbines that you can see offshore. How do you get the power to shore? That's where us cable guys come in, the hidden fruit. You can't see us. Once it's installed, you'll never see it again, but we are obviously integral to the power export of the export of power from the offshore systems. So the role of the submarine cable, historically they linked shore-based power grids across bays and estuaries and rivers. There's very old hat, it's been done for a long time. They also carry power between countries, so interconnectors. There's many interconnectors between Europe and the UK, for example. They also transmit power to offshore installations such as oil and gas platforms, as you can see in the bottom right there. But also now more and more popular is exporting power from the offshore generation assets. So how do we get there? Now, the process of going from a conceptual, hang on, Scottish Power want to build a wind farm somewhere, is a very, very long process. Now, just to give you an idea of scale, EA3, we started working on EA3 to develop the consent, so just achieve a consent from the government, I think as far back as 2011, possibly 2012. We achieved consent in 2017, and now we're starting construction of the project in 2024. So there's a very long timeline. So, 10 plus years to go from the concept of an offshore power generating system to actually physically delivering it. A lot of that is paperwork, and a lot of that takes a huge amount of effort and man hours to actually deliver a project of this scale. So on the right here, I've got an idea of just the sort of process you go through to get a wind farm from securing a site through to actually being fully operational. And as you can see on the screen here, we've got minus 48 months. So it's looking at a site, where's a good wind yield? So that's where it starts from. Where's a good area in the sea that has a good wind yield? That's identified. We then move through into initial feasibility study. So we look at the water depth. We look at obviously the geotechnical conditions. We look at the met ocean conditions, see, right, is it good? We then go to consent. So are we going to be allowed to build a wind farm here? You see the timeline on this table I've included here. It goes all the way through to 0. So that's when we've secured the investment. We've gone through the tender process. We've got contractors to build our wind farm for us. And now we're going to start construction. And then construction can take nearly 3 years to build a wind farm of the size we're building on the A3. And that's involving securing the supply chain, and then securing, just the steel for the monopile foundations or the jacket foundations for the wind turbine structures. Thousands of tons of steel has to be secured. If you think the drawdown on the steel supply in the world, when there's all these wind farms with these massive steel structures being constructed, is quite significant. So this, I've taken a screen grab of a previous project to work on. I think this is EA1. Now this is just, I'm not going to bore you too long, so please don't panic and leave the presentation. But this is a screen grab of the main document register we had at the end of the project. So this is the list of documents required to achieve the engineering deliverables to actually physically install a cable offshore. Now, I think last time I counted it, it was over 176 documents, and these can vary from, the schedule. Obviously, it's very important in any project, but route position listings, crossing design, so when we cross other assets subsea, all the way through to crew transfer procedure. So it's a very big engineering task just to get the cable ships offshore to install. So from an engineering perspective, I find it very interesting because it's so broad ranging. You're dealing with structural engineering, you're dealing with ocean engineering, and it's a really exciting subject, especially for new engineers that are moving from graduation into opportunities to move into professional life. It's something I'd really advocate for people to get into. So how do we install offshore cables? The key thing with cable installation, you use what's called an installation analysis software called Orcaflex. Now this allows the analysis of static and dynamic installation operations. So bearing in mind, we've got an export cable that could be, say, between maybe 300 millimeter across diameter, so as big as your waist, depending on how good Christmas was. It's obviously a stiff object. Now this has to be deployed over the back of a vessel and then pulled into an offshore structure. Now, how do you make sure that the integrity of that cable is maintained throughout the life cycle when it's a dynamic environment? The vessel's moving up all the time, the vessel's paying out cable, the vessel's moving along the sea, the cable's laying on the seabed and it's bouncing. It's all dynamic, not conducive for a rigid body to be exposed to. So Orcaflex allows the analysis of this by breaking down the cable into component parts or small nodules. And you can run Orcaflex to simulate very, very precisely the activities you're performing offshore. So the first one I've got here is, and I've got a video to demonstrate it, is the cable pull into land and offshore structures. So the picture on your right here, imagine this is your substation. This is what's called a J-tube. So your offshore cable needs to be pulled into the substation, and then it's terminated into the switchgear on the substation, which then connects it to the array cables, which then connect you to the wind turbine generators. So being the single point of failure, your export cable, it's very important to look after it like a newborn child. It has to be taken care of. It's very sensitive. it's copper, it's lead, it's fiber optic, it's many components that aren't particularly conducive to bendy operations. Now, the way this is done is we perform the simulation in Orcaflex, and it's built up, and it takes a very long time to run the simulation, but I've got a good video here which hopefully works. Good. This shows you the output of an Orcaflex analysis. Now, this is the cable being pulled into the J-tube, which I just showed you. Now, this is all run in this simulation called Orcaflex, and it gives you tension, bending moment, and speed at which the installation can be carried out. And you can see here that it takes a long time to build this up, and then it can take days to run the simulation. So you usually have to leave the supercomputers running over a couple of days to get this analysis completed. And then the output will give you your installation parameters. So the maximum wave heights you're allowed to install the cable in, the maximum tension you're allowed to expose the cable to. And this will guide your installation parameters and the allowable limits that the cable can be exposed to during the installation. So each one of these little points you can see is each nodule of that cable being pulled into the J-tube system. Now, the distance the J-tubes can be from the seabed could be up to 60 meters. So you have a big export cable that can weigh approximately, between 40 and 50 kilos per meter, being pulled in 60 meters up in a vertical orientation. So there's a fair bit of load going through that cable as you pull it in. And then it's being pulled around radiuses as well. So it's being exposed to different moments as it's pulled around these radiuses. So it's very important to complete these installation analysis to make sure that your cable is going to be safe and secure when you put it in. Now, other activities that are modelled in the offshore installation would be your general lay as well. So just laying the cable off the back of a ship, but also the joint installation, which is very important, as you can see the picture in the bottom right here. Now, joint installation, we can't have 147 kilometers of cable on a ship. It just physically wouldn't fit. So on this project, for example, we're installing 75 kilometers of cable to start with. We then go back to the factory, pick up the additional cable, come back, and we have to joint it offshore. Now, to join an HVDC cable, you allow between 7 and 10 days offshore time to actually physically joint the two systems together. It then has to be tested. Once it's tested, it then gets overboarded by the vessel. Now, you can see here they're overboarded with what's usually a spreader frame with a complex rigging situation to try and avoid any additional forces going through that joint. Now, bearing in mind 7 to 10 days jointing activity, you do not want to have to repeat that. So it's very important that you run the Orcaflex analysis to understand your installation parameters to allow you to install that safely and avoid you having to repeat a 10-day jointing time. Now, just to put it into context, if you think a vessel that will be installing our cables probably costs about £150,000 a day to charter, 10 days of vessel time is a fair whack of money that we do not want to spend. So it's so important that this activity is done very well, very safely, and very securely. Now, as I said, we've got cable pull into land and offshore structures, the joint installation, and the general lay. The analysis includes also survival analysis during vessel standby operations. So if you think maybe 147 kilometer cable is going to take probably 3 to 4 weeks to install, we can't guarantee that we've got perfectly flat, calm weather in the North Sea for 3 to 4 weeks. So what is survival analysis? So that's where you look at the cable in a general lay scenario and say, what is the worst case scenario this cable can survive without damaging its properties and us having to cut it and joint it at a later date. So the survival analysis basically simulates the worst case weather conditions that the vessel can take with the cable deployed from the stern. We then look at that and bring it down a margin and say, okay, we're comfortable. The vessel can be exposed to, let's say, 3 meter wave height for an extended period of time. Anything above that will then compromise the cable's integrity. And there's a couple of situations you have to look at. One, if you're stuck on weather for a long time, you have to cycle the touchdown point. So hopefully everyone can see on the camera here, imagine you've got a piece of string hanging off the back of a vessel in a nice arc. That touchdown point where it touches the seabed is seeing fatigue. If you're staying in that position, the fatigue life of that cable has been assessed. You have to cycle it, so you have to move the cable backwards and forwards with the vessel to move that fatigue point away from the same area all the time, or you're going to exceed the fatigue life of the cable. We look at curve stability analysis to ensure the cable remains on the route position listing during cable lay. So in an ideal world, I could lay from A to B, so our landing point to our offshore substation would be a complete straight line. That's not the reality. We have to lay radiuses. So when you're laying a radius with a cable, if you've got a smooth seabed, how do you guarantee that radius isn't going to be pulled out when you're going around the corner? And that's where we look at the stability to make sure it stays in place. So the tension it's exposed to on that radius by the vessel induced tension doesn't allow that radius to be pulled out and end up with a cable that's too tight and goes in a straight line. We also look at the abandonment and recovery analysis in case of lowering and retrieving a cable from the seabed. So in the instance of planned joints, we get to the end of the cable. What do we do with it while we go off and pick up our remaining cable? We have to lower it to the seabed. In this instance, the cable's rigged up with rigging systems and it's deployed by the vessel crane to the seabed. But we have to then look at that activity and make sure the cable's integrity is maintained by running the Orcaflex analysis, repeating exactly basically what the vessel will do, making sure the cable's not being exposed to undue stress in the environment. And then finally, the general lay analysis is to ensure the vessel knows at what layback range the cable can be installed and under which environmental conditions. So the layback is the distance of the cable from the rear of the vessel to the touchdown point, as I mentioned earlier, and that can really change a lot depending on the water depth. So traditionally at the moment, we're working on fixed bottom wind, which has maybe a depth range of about up to 50, 60 meters. But as we move into the offshore floating wind, it's going to be a very different scenario where we're going to have 100, 150, 200 meter water depths, if not more. So that general lay and the tension the cable's exposed to in offshore floating wind is going to be a lot more significant than it is at the moment with the fixed bottom structures we're working to right now. So this is a very quick simulation giving you the Orcaflex outputs of a cable lay vessel installing in general normal lay. So you can see hopefully in the video that you can see the tension. So the effective tension on the axis there of the graph over time. So as that cable's installed, you can see what tension the cable's realizing as it's installed in that certain activity. And you can see here there's some peak tensions of over 120 up to 130 kilonewtons. So it's not insignificant. And that's in a relatively benign condition. Now, if you think that you have a short wave period at a relatively high wave and the vessel's bouncing up and down quite quickly, those tensions are going to increase. So the dynamic exposure to that cable is quite significant again, which is why we also look at the general lay and weather parameters in the Orcaflex systems. So the other output of the cable installation analysis is providing a form of lay tables. So they basically give you the workable weather windows for each operation. Now, if you've never seen one of these before, it takes a little while to get your head around it. But what we have on the right is a wave rose. It gives you the water depth you're going to be operating at and your operability for the vessel. So depending on which orientation your vessel is in, will give you the maximum wave height your vessel can perform that installation at. So if we take a nominal, if you look at the orange line, stage 1 in the table, we can see heading. We take off 0 degree heading, which is to the north here. We've got the orange line, which gives us stage 1. So that gives us our maximum wave height workability of 2.75 meters. So in that particular activity, we know if we're in that heading, in those wave conditions, we're safe to install our cable up to 2.75 meter wave height. Anything more would start to compromise the integrity of the cable. We'd have to either look at adjusting our vessel's vessel heading or look into the survival analysis if the weather's picking up too much. Now, the analysis considers all factors that a vessel can be exposed to in the dynamic environment. We've not only got wind, we've got current, wave height, wave period, the vessel characteristics and the vessel position. Now, not all vessels are made equal. The design of the vessel has a big impact on the way it behaves in the water. you could have, for example, a flat-bottomed vessel that's designed to come as close to shore as possible. As you'd imagine, has very poor seakeeping ability, so its performance when it's installed in cables is potentially compromised. But then when you're coming to a landfall section where you have very shallow water, obviously having that flat-bottomed vessel is much better. Now, if you have a deep drafted vessel, its seakeeping operability is a lot better, but then you compromise the access to shore for installing a cable into the shore side. So there's pros and cons for different vessel designs, and that's why we run the analysis based on particular vessel characteristics. So you get a set of characteristics for each vessel, which is supplied by the naval architect that designs it, and they also do, you know, like small scale testing to get these sets of parameters, which then feed into the Orcaflex analysis and then feed into your installation conditions that are allowed during cable installation. So cable route engineering. So we've got our offshore substation at A, and we've got our landfall point at B. How do we get there? Now, first of all, the route engineering requires full seabed surveys. So this includes geotechnical surveys, so cone penetration testing and boreholes, multi-beam echo sounder, side scan sonar, sub-bottom profiler, and UXO magnetometer. And I'll just run you through each one of these. Geotechnical conditions. Why would we need geotechnical conditions for a cable installation? Number one, cable thermal performance. How does the cable perform in the conditions we have on site? For example, if you have high thermal resistivity soils, such as clays, that are maybe a 0.7, 0.8 TR value, that's really bad for your cable. If you have low TR value soils, such as sand, that helps dissipate the heat away from the cable, so the cable's performance is improved. So if you have, to cut a long story short, if you have a high TR soil, you tend to have a bigger cable to help radiate the heat away from the cable. If you have a low TR soil, you can get away with a smaller cross-sectional cable because the thermal performance is much improved. Now, the pictures you can see on the right here and the left. On the left-hand side is a UXO target list. Now, why would we have this? Well, East Anglia 1 and East Anglia 2 export cables actually run to the north of a munitions disposal zone. What is this, you ask? Well, this is where German and UK-based bombers would drop their payloads if they hadn't dropped them over the respective country. So in this area, we've got mines, unexploded bombs, all sorts of different stuff that was dropped there years and years and years ago. Now, that's obviously in a dynamic environment. The sea moves, there's currents, there's mobile sediment. So this munitions aren't just located in this munitions disposal zone, it gets spread all over the North Sea. Now, we have to do, as I say here, the UXO magnetometer is one of the most important surveys we do, because we have to identify whether there are any potential unexploded bombs on our route. Now, the left-hand picture you can see are potential UXOs that have been identified by our magnetometer surveys. Now, a potential UXO is something that has a metal signature that could potentially be a bomb or a mine. Now, we have specialist UXO consultants that we use. They interpret the magnetometer data. They look at it against other known munitions that have been found previously and say, right, that is a potential UXO. We need to investigate that or avoid it. If we can't avoid it with our cable route, we then have to go and investigate it. The picture on the right is a post-installation investigation. So it shows you where we have actually positively identified UXOs on the cable route. For East Anglia 1, we had to investigate 1,500 potential UXOs on the wind farm and the cable route itself. Now, this is mostly done with remote operated vehicles, but in the shallow areas, we had to use divers as well. I can't remember how many explosions we had to do in the end, but there's a fair few. I worked on Greater Gabbard project. I was working as a dive engineer at the time. And fortunate enough, I had a number of ex-Royal Navy clearance divers in my dive team. We were diving on one of the monopiles, and he came through on the radio very calm and said, there's a XYZ German 1,000-pound bomb rolled up against the monopile. And we're like, what? Right, and we're like, who's down? That's Bob. Okay, Bob's an ex-clearance diver. He definitely knows what this is. And it was a 1,000-pound German ground mine that had rolled up against our monopile whilst our guys were down there diving. So we then had to come up with a plan of how do we get rid of this, because we can't dispose of this bomb that's rolled up against an asset. We've got a 10 megawatt turbine on top of it. What do we do? So we had to work with our UXO disposal consultants to come up with a plan to move this mine and then blow it up further away from the wind farm. Now we ended up blowing it up. The vessel had to be 1 nautical mile away from this mine because it was so big that it could rupture the propeller seals around the prop shaft. And it was quite an exciting thing to be working on, but also quite shocking when you're in the middle of a day's work and there's a very significant explosive that's rolled into your work site. So that's why we have to clear them. Obviously, we have to provide a safe site for our installation contractors to work on. And it's the employer's responsibility, Scottish Power's responsibility, to provide a safe site. So we never get our installation contractors to do the UXO removals. It's always down to the company, so Scottish Power in this instance, to make sure there's a safe work site. And we will then pass on an ALARP certificate to our installation contractor saying, this is now a safe work site for you to complete your scoping. So here I've got a screen grab of what's called the route engineering flowchart. So this is how you design a cable route. As you can, I'm not going to go through section by section, but you start off with the survey data. You start off putting an initial route position list. So that's you plotting your 147 kilometers across the cable route. You then look at what seabed features we have. Do we have big sand waves? Do we have rock? How are we going to protect this cable? We then go back and do a PUXO survey. Right, can we avoid anything? Okay, if we can avoid a PUXO, we then avoid it, reroute it, go around it. And then we finally go through this almost 3 RPLs we usually have to a finalized RPL, which we then have to go and clear the bombs if we found any, and design the dredging volumes. And then the output will be a cable installation along a defined route with a clear and safe corridor. So cable route preparation. As I said, we've designed the route, we've done a paperwork exercise, we've done the surveys. What do we do next? So boulder clearance. Now, we're relatively fortunate in the East Anglia region that we don't have a huge issue with boulders. But if you go further up to the Humber, there's a lot of glacial till, which can play havoc with your installation solutions. So what do? When you've got a small number of boulders, we use what's called a boulder grab, which is the system on the right you can see with the almost like the 50p machine you get in an arcade where you never win a teddy. But in this instant, I think this one can clear 5-ton boulders from the cable route. Now, the other more agricultural solution when you have big issues like glacial till, where you just need to clear a huge volume of large boulders out of the way, is what's called a scar plough. It's called a scar plough because it leaves a big scar in the seabed. Now, just to give you an idea of the size of this piece of machinery, this is actually a human to the top right of this. Hopefully you can see my pointer. So what happens with the scar plough? It gets deployed from the back of a very big tug. So a tug that usually manages the anchors on an oil rig, for example, and it's towed along the seabed at very high tension, and it basically just sheds the boulders out of the way to then allow you to have a clear passage for the cable to be installed. Like I said, it's very agricultural, but it's really only one of the real solutions when you're working in that glacial till to actually achieve a decent burial scenario. What's integral to a pre-cable installation is called a pre-lay grapnel run, so a PLGR. This is used to clear debris from the route, including fishing nets, ropes, and other submerged debris. You can see the drawing at the bottom is a standard grapnel train configuration. So it's a system of hooks basically that are designed to be run along the seabed. They penetrate about ½ a meter, maybe up to a meter, depending on the soil conditions. They're designed just to remove any linear obstructions, particularly fishing nets and ropes that could cause you a big issue during cable installation. These are usually done on the back of an anchor handling tug again, and they're towed along the route usually a week or 2 weeks before the cable installation campaign starts, just to make sure that you've got a nice clear site to allow you to install the cable. Obviously, if you're trying to install the cable over a linear obstruction, you're not going to be able to protect the cable because it's going to stop itself being buried. So that's a really integral part for the cable route preparation. What other issues we have? So East Anglia 1, we had mobile sand waves up to 12 meters in height. Now, when you want to protect a cable, usually we protect a cable by burying it about 1 meter in the seabed, maybe 1.5 meters. But there's no point burying a cable in a mobile seabed because, you know, in a number of weeks that seabed's going to have moved. And what happens, as you can see the drawing on the left here, you've got the existing seabed in red, and then you've got the design seabed. Now, if we install a cable 1 meter below the existing seabed, in a few weeks' time, that sound wave's going to have moved, and we have a big bite of cable, almost an omega-shaped cable sticking in the seabed, which is very, very popular for fishermen to accidentally get hold of when they're doing trawl. So that's something we don't want to do. So what do we have to do to mitigate this? We have to dredge out a channel in the seabed. So as a civil engineer may design a road through a rolling countryside, similar scenarios, you can see the figure on the right. You dredge a channel through the sound waves to give you a design seabed, which is at the stable seabed level. So we know if we bury our cable below that level, it's not going to get exposed over the lifetime of the project. Now, to do that on East Anglia 1, we used, I'll show you later on, a very big vessel called the Francis Beaufort. You have to remove the seabed features along the export route and make sure it's buried nice and safe, reduce the risk of the cable becoming exposed by the movement of the sound waves, and the dredge trench through the sound waves to mean seabed level, as I said. We then bury the cable in the seabed using a plough or trencher. Now, this is the Francis Beaufort. As I was saying, it's called a trailing suction hopper dredger. You can see here on the right, imagine your Dyson at home, but on a supersized scale. You've got the Dyson head with all your brushes in it at the end. This gets dragged along the seabed, and then you've got the big motor here or pump that basically sucks up the sand in the seabed. Now this drag head, this is called, and then you've got the suction pipe and the hopper. Basically the trailing suction hopper dredger is a common dredging vessel, seagoing self-repaired dredging vessel that is suitable to dredge silty sand and gravelly soils or soft clay. This one I think has a hopper capacity of 15,000 meters cubed. So she can suck up about 15,000 meters cubed before she has to transit off to the dumping site. Then she has doors on the bottom which open up and she deposits the sand and comes back and basically hoovers your channel through the mobile sediments. Other issues we have, I don't know if anyone's ever seen a map, but there's an interesting website called Kiss Orca, which I can put in the chat afterwards, but it basically gives you an idea of the number of utilities or third-party assets on the seabed. If you're looking at the east coast of the UK, between UK and Europe, you'd be blown away by how many cables there are. Power cables, interconnector cables, fiber optic cables, transatlantic cables, you name it, they're there. We obviously can't cut through these, so we have to cross them. How do we cross them? Well, we have to do a crossing design. Now, cable crossings are needed when a new cable, like EA3, crosses existing infrastructure. As I said, power cables, oil and gas pipelines, or fiber optic cables. We can build the crossings either out of mattresses, which are concrete mattresses. They're 6 meters by, I think, 3 meters, and they're basically put over the top of the cable as a protective armor, essentially. Or we can have what's called rock dump. So you can see here the example with the mattresses. And then we have a rock dump, which is basically a berm, which is laid over the top of the cable post installation. Now, the purpose of this is to protect it mostly from fishing activity, but also errant anchor strikes, should a vessel be in trouble and they drop their anchor, or a vessel drags over the top of it, to make sure you don't catch your cable and rip it out the ground, basically. Few key engineering design considerations. So obviously we have currents. You have what's called scour. So when you have a fixed object on the seabed, the way the currents work can lead to scour around that object. So you could lead to a very big hole. The current basically makes a big hole around that object and it makes it unstable. So we have to do scour assessments and make sure we do hydrodynamic design considerations, including the design of these. We've now got concrete mattresses that have fronds on them. So it's basically almost looks like artificial seaweed. And the way they do it, they deploy it and they release these fronds which float up above the mattress, and they're designed to trap sediment in the fronds themselves. So you almost make an artificial sand berm over the top of the cable, and they work very well. And then you've obviously got the rock design, which is pretty agricultural, but it does the job as well. So crossing design must minimize scour, maintain a stable structure for the expected level of weather, current, wave, and other environmental forces, as well as the fishing activity I mentioned earlier. So next, we cleared the route. There's no bombs, there's no obstructions. We've prepped our crossings. What do we do next? Well, we have to get the cable from the factory. Now, Europe's quite lucky in respect that we have quite a number of cable factories. We've got them in Italy, Norway, Sweden, some in the UK, more in the UK being developed now, which has been recently announced in the news. How do we get the cables from the factory onto the vessel? Factory load cables directly onto installation vessels or transport vessels as required. The factory and the cable lay vessel need to work in union to make sure the integrity is maintained throughout the loadout operations. Loadouts can take days or even weeks in the case of transcontinental fibre projects. So in our instance, EA1, I think we were 85 kilometres long. We had 2 loadouts. Each loadout was between 5 and 7 days just to get the cable out of the factory onto the ship. So it's quite a big activity and undertaking. As you can see in the diagram I've got at the bottom there, we've got the green land feeding system. So this is the factory. They have a storage carousel or turntable. We then have a very long factory cableway, which basically looks like a series of mini roller coasters that come from the factory storage area all the way through the factory, round the outside, onto the quay side, and then onto a chute to then prepare itself for being added onto the cable lay vessel. We have what's called a tensioner, which induces tension on the cable, so it pulls the cable along. It looks like a big caterpillar track, which sandwiches the cable in between it. And then you have the cable catenary, so that's the quay side. You can see here, this is the interface between the vessel and the land-based cable factory. Then have the chute or laying wheel and a tensioner on the vessel, and then a loading arm on the vessel, which loads the cable into the carousel. Now, here's a good example. This is Nexans loadout between Nexans factory here, and then I believe it was Deep Ocean's CLV, the Maersk connector. And you can see the sheer size. I think it's a 5,000 ton carousel on the Maersk connector. You can see 4 humans there loading out this cable. And as I said, they'll be working 12-hour shifts, non-stop, night and day, for 5 to 7 days to load that cable. And it's quite hard physical work as well. So these guys have big levers. They basically look like shovel handles with a paddle on the end, and they have to make sure that that cable's nesting perfectly as it goes on board. Otherwise, you don't have enough capacity to load out as much cable as you can. So it's very tightly packed, and it's quite an important operation for the guys to achieve a good nesting. So here is an example of the same factory here, Nexans factory in Norway. It's probably one of the most picturesque loadout points you can go to. It's not bad. It's right in a fjord. Nexans beautiful scenic loadout fort. You can see the cable lay vessels moored up against the factory. She's got preset anchors, and it's very important that the vessel holds position for that extended duration. If you have a weather system come in, the vessel can be exposed to a dynamic environment. It could cause issues with the cable. So to do this, again, another engineering feature is we have to do a mooring analysis to make sure there's safe conditions should the weather change. Landfall. So landfall, where the cable comes from the sea to the land, as it's pretty self-explanatory. It's one of the most technically challenging aspects of cable installation. It can be made in a variety of ways, depending on the seabed topography and the onshore coastal conditions. The 3 options that are mainly looked at are open cut trenches, HCDs, and micro-tunneling. Landfall open cut trench is probably the simplest solution. It's the cheapest, less risky, but it's only feasible when there are no environmental or physical restrictions such as seawalls. As you can see here in the picture, basically it's a sand dune. There's no real limiting factors other than a big sand dune in the way. The company that have installed this cable have just basically dug a hole through the sand dune, and they can pull the cable off the cable installation vessel you can see in the background there, along the beach, and then up these rollers with a big winch, a winch, probably about 50-ton winch. More technically challenging, landfall, horizontal directional drilling. So this is oil and gas-based technology, but deployed in a horizontal direction. It's becoming the go-to solution offshore wind and subsea interconnector projects. It has an increased risk. It's technically challenging. Without knowledge of the soil conditions, you don't know if you can actually do an HDD. So clay, for example, is good for HDD. Rock is good. Shale, shingle, gravel, really bad. So unless you have good geotechnical data, it's very tricky to commit to an HDD without knowing what the conditions are. HDD lengths can range from 50 to 150 meters, and that really has an impact on how much tensile capacity the cable can withstand. Site conditions need to be favourable, and the HDP pipe. So this is the HDP pipe we used for East Anglia 1, being towed from Norway. That is 1.2 kilometres long, and there was four of them, sorry, being towed by a tug. So they had to tug this from Norway all the way down to the east coast, which is a feat on its own. Now, landfall HDDs can be executed in two ways. You can drill from onshore to offshore and then pull the duct in from offshore. So you need offshore support vessels. Or you can drill onshore to offshore. Basically push the duct in with a big tensioner, you can see in these drawings here. So basically you drill a pilot hole, you expand that hole, and then once you get to the size of hole you need, you can then practically inject the HDPE pipe into the hole. This is good for about up to 750 meters. This tensioner that pushes the pipe into the hole is probably rated, I think, 150-ton tensioner. I've got a good graphic to show you on this one here. This is from the Changhua project I did in Taiwan, about 2019. See, we had 3 HDP ducts. They ended up being 750 meters long each. We were executing from an area of reclaimed land that had a large seawall around it, so we couldn't cut a hole through the seawall. The reclaimed land you can see here was actually lower than high tide, so there's risk of it flooding. So obviously breaching the seawall wasn't an option. So the only real solution was HDD. You can see here the drill rig starting with the pilot hole. So that's basically the smallest OD drill pipe they have with the cutting head on it. It's the first pass, and that basically gets you your gauge and your ideal trajectory for your pipe. See here, we go down deeper into the more consolidated layers of soil, which gives you more a better chance of a well-executed project, less chance of collapse. We then pull back the drill bit assembly and increase the size to expand the hole out. This is the reamer. So this then expands the hole. And depending on the size of the HDPE pipe you want to insert into here, would depend on how many reaming passes you need to do. A lot of the time, if it's up to, I think, 600 to 800 mil pipe, you can get away with 2 reaming passes. Okay, so the barrel reamer is designed to clear out the hole, so it just clears out any debris, making sure you've got a clean hole ready for insertion of the HDPE pipe. And the beauty of this operation is we have really bad weather conditions in Taiwan, and the Taiwan legislation did not allow us to do onshore HDD works in the summer months. So we had to execute it in the winter months, but the offshore weather was so bad we couldn't have a weather window for offshore support. So we came to this company, Van Leeuwen, who is a Dutch company, who have this patented insertion technology. There's only a couple of countries in the world, companies in the world that do it, but they could execute this scope without any offshore support whatsoever, which was the key driver for us. As you can see, that's been inserted into the hole. That's now ready for cable installation at a later date. Just putting in the heavy chain and plug to make sure we don't drain the China Sea. And then when we came to cable installation, the cable lay vessel and its support vessels retrieved the end of that HDPE pipe above the surface of the water and pulled the cables into it. So the final solution is direct pipe or micro tunneling, or pipe jacking as it's known. This is a very good solution when conditions are unsuitable for HDD or open cut trench. It's very, very expensive. Basically, the way micro tunneling works, you have what's called a pipe jack, which you can see in these pictures here, and you weld on sections of steel pipe at the OD you require. It has a drilling rig on the end of it. You can see this bottom right-hand picture. This is the drill head. So imagine Crossrail project on a smaller scale, so a micro scale. You have your drill rig on the end of it, and you weld on sections of steel pipe as you go, and a big set of pneumatic pushers basically push this drill rig through the ground until you get to the point of extraction. Couple of issues with this. The older technology, when I was looking at it for EA1, they still had to send a human down the pipe to sever the electrical and hydraulic connections when you had to recover this pipe from subsea. And we were like, we can't tolerate that. You need to come up with a better solution. Apparently now they have remote systems to sever these connections, but it was a little bit agricultural at the time, and it didn't pass our HSE, as you can expect. Like I said, it's very expensive. You're looking up to about 1,000 meter range on these, I believe, but I've never actually physically worked on a project that's executed using these ideas. They're very common in oil and gas because they're a bigger OD pipe and they're good for pulling oil and gas pipes inside. Okay, moving on, cable lay vessels. So the key system we need to achieve installation. Purpose-built ships and barges accurately place cables on or beneath the seabed, guided by the route survey. There's a large variety of ship types for different applications. We've got export cables, so big OD cables, array cables, which are the smaller cables that link up the offshore wind turbine generators with each other in a daisy chain configuration, and they also bring the power into the offshore substation. We've got HVDC interconnectors joining continents and fibre optics. Now, this is the Maersk connector used to do East Anglia 1. As you can see, she's large capacity carousel. She's actually at 7,000 ton carousel, flat bottom, shallow draft. So you've got some sea keeping, negative points for sea keeping, but she's beachable. So she's very well designed for export cables where you know you're going to have to make a beach landing. This is, I think, a Northeast project. It might have been the Hornsey project she was on. You can see she's completely aground, perfectly designed for this solution, and a very stable platform to do the landfall pulling of the cable. Array cable vessels, so they have CPS storage, so cable protection systems, which you need to secure the cable in the J tubes on the offshore structures. They have dynamic quadrants and smaller carousels because the array cables are smaller. Your interconnector vessels, which have large multiple carousels. So this is a Nexans Aurora. She's got two 7,000 ton carousels. She's got dual firing lines, so she can install bundled HVDC cables. So you have the plus and minus poles, and they can also bundle a fibre optic cable into it as well, which we're doing on East Anglia 3, and have a very long endurance. So with the big capacity carousels, you can put more cable in, less visits to shore equals more efficient, cost effective. And then you have barges. So you've got dun barges and motorised barges, shallow bottom barge for landfall and shallow water works. They're usually operated by anchors and tugs. Smaller carousel to keep vessel weight down and shallow draft. So these are very good for smaller projects or landfall sections where it's particularly shallow for long periods. So you can't bring in the bigger cable lay vessels. The CLVs can be operated in multiple ways. So you've got the conventional prop and rudder. You've got the dynamic positioning systems and anchors and tugs. Dynamic position systems, for people that don't know, is a computer controlled system to automatically maintain a vessel's position and heading by using its own propellers and thrusters. It has a positional accuracy of up to 10 centimeters, which is pretty phenomenal. So if you think you're parked alongside an offshore substation, you want a very, very precise positioning of your vessel. So it takes in multiple satellite systems, weather sensors to give you that precise system, and it is very good. The cable lay equipment that you'll find on these vessels, again, you've got the carousel, main loading arm, which loads the cables into it. All offshore cable lay vessels have a crane. The quadrant, which is used for deploying the cable to the seabed. We've got the chute to make sure the OD of the cable is maintained, and the tensioners to maintain the tension, and then a jointing container required for jointing the cables when you've got two or more sections. The carousel, as you can see here, come in various sizes, 7,000 ton twin lay carousels on these big HVDC interconnector vessels, down to, sort of 100, 200 ton array cable vessels that only need to have a small load capacity. The carousel packing calculations are required, as I said earlier when I showed you the loadout slides, to ensure that you can fit as much cable on your carousel as possible. You do a packing calculation, which gives you an idea of the length of cable you can fit on there, depending on the OD and the weight, and also how well you're packing it. So this is a perfectly packed cable, and it sounds like a very boring subject, but it's very, very important, because if you said, I can fit 7,000 tons of cable on your ship and you haven't packed it very well, you may have a couple of kilometers left over and no one's going to be very happy about that. These are the tensioners. As I said, they're Caterpillar track tensioners. So these basically apply a squeeze to the cable as you're installing it, and they roll through, adjusting the tension as you go to make sure that the cable's installed with a good residual bottom tension to allow it to be installed safely and securely. Chute and capstan wheels. As I said, the chute, this is probably a 10-meter MBR. So a cable has a minimum bending radius for installation. You do not want to exceed that minimum bending radius, because you can start compromising the components of the cable. So European tend to have the chute you can see on the left. The Norwegians are big fans of the capstan winch, which is really looking after your cable. So Nexans are a big cable manufacturer. All their vessels have capstan wheels on them, and it's seen to be very, very nice to the cable. It's kind of the Rolls Royce of cable installation. ROV, so remote operated vehicles. If you've not seen one of these before, this is called a work class ROV, and they're used for observation of the cable, touchdown point, and intervention during the cable lay. They're high powered for station keeping in high currents. They use manipulators for assisting with recovery of messenger wires and cable protection system installation. They're used for subsea connection and disconnection, mattress installation, and recovery of lost equipment. As you can see there, they're about the size of a small car, maybe a Fiat 500, and very complex systems that like to break down quite often. Cranes, as I said earlier, I won't go on too much about this, but a very integral part for obviously loading out systems onto the boat, but also deploying the cable to the seabed when you've joined it, and obviously moving things around on the vessel itself. And the quadrant, as I said, you've got to treat the cable like a newborn baby. The quadrants are used in a number of applications, managing the cable on the deck through the lay system, but also deploying the cable to the seabed at your offshore structures. And the point of the quadrant is to make sure you maintain the MBR of the cable as you deploy it in the water column, and you lay it down, and it's called tripping the quadrant, where the quadrant's laid down in a vertical orientation. The vessel steps away and lays the quadrant down gently. The cable falls out, and it's all nice and looked after. Then finally, cable pulling. Cable pulling to landfall. So I've shown you the solutions at landfall. We've got HDD, open cut trench, and micro tunneling. I love this picture because it actually gives you an example of pretty much all the situations you may occur. So we've got an HDD entrance here. We've got the ship here with a floating cable down to a vessel that's at the entrance to the HDD. This vessel then feeds the cable into the HDD, which is then being pulled by a winch into this transition joint bay here. So I think it's a good example to show you the complex scenario at landfall, where you've got a vessel paying out cable, you've got an onshore team paying in on the winch, you've got dynamic environment. So obviously you can see the currents running north to south here. So there's a big bow of cable because of the current. And that dynamic environment's all been run through Orcaflex to make sure that cable is going to be safe and secure in that environment and those conditions that are expected to occur at that landfall operation. It's a typical landfall setup. So we've got our pulling winch onshore, we've got our sea defence, we've got our cable lay vessel, and we've got our support barge, be it a jack up or a spud leg barge, something like that. We position the support barge at the entrance to the HDD. HDD lengths can vary, as I said earlier, between 50 to 1,500 meters in length. We've then got a very high powered winch to pull the cable in. So we feed the cable through the HDD onto the barge. The cable lay vessel feeds the cable from the vessel onto the barge here, connect it up to the pulling winch, and then commence pulling in from onshore. So again, this is a bit like a ballet. You've got numerous activities happening in parallel with one central point of contact running this show. You've got usually the installation supervisor or superintendent will be coordinating all the activities to make sure that they're paying in at the right speed on the winch, they're paying out at the right speed on the vessel. The tender vessels that are looking after this cable catenary are in the right place. They're making sure the cable's not having too much tension on it. So it's a very complex operation, very exciting, but also very challenging from an engineering perspective, but very fun when you do it right. So here's actually the East Anglia 1 cable. Like I said, I think it was a 1200 meter pull-in. We saw tension on this cable in excess of 50 tons during pull-in. Give you an idea, in the very distance here is the Maersk connector, which is the vessel I showed you that beached. So she's maybe 1200 meters away, and that cable is connected to the Maersk connector and being pulled into our transition joint bay here. And here's a very happy cable design engineer to show you the size of this cable that's pulled in and successful operation. We also have to pull the cable into the offshore substation. Again, another tricky part of the offshore cable installation. They can be pulled in as a first or second end. So the simplest solution is to pull up there in the cable lay vessel and deploy the end of the cable straight off the vessel into the substation through the J tubes, which I showed you in your Yorkerflex analysis earlier. Or the more slightly trickier is if you're laying from the landfall end to the substation, you then have to deploy the cable onto the seabed in a bight, and then do what's called a second end pull-in, where you lay the bight on the seabed, you connect your winch on the substation and pull the cable in using the quadrant and the bight to slowly pay out the cable from the quadrant into the substation and hopefully have a nice straight cable route as you approach it. You can see here, this is a cable installation operation using a quadrant on, I think it's the Van Ord vessel I showed you earlier, the array cable vessel. See, she's deployed the array cable on the quadrant from the back of the ship. She's deployed the quadrant through the water column, and she'll deploy it onto the seabed as the winch in this instance, it's a turbine. As the winch on the turbine's pulling this cable in, this quadrant's laid on the seabed and gently lays it down, and hopefully you have a nice clean transition. And then finally, cable system accessories. So as I said earlier, the joints, offshore joints join the two cable sections together. They can be completed in Amiga format. Configuration is shown to the right. So this joint will end up with an Amiga shape on the seabed. Or you can do what's called an inline joint, where you join the vessel on the vessel, you join the cable system, but then carry on laying as normal. So it's an inline joint, and you don't have that Amiga shape on the seabed. As I said, offshore export cable joints can take between 5 and 7 days, up to 10 days, depending on the weather, and is relatively complex activity. It has to be done in a sealed habitat as well, so making sure there's no material or dirt or anything introduced into the joint while they're sealing it, and then it's heavily tested before deployment. And then finally, the cable protection system. So the transition from seabed into the structure, you need a cable protection system which protects the cable and maintains the integrity of the cable for the lifetime of the project. The design should take into account hydrodynamic forces, effects of scour, and the thermal impact on the cable when you install it. So this cable protection system you can see here, this is the entrance of the the J tube on the on the offshore substation. You pull the cable protection system into this bell mouth, and it locks in place in this instance with this ball and taper technology, which is a patented technology from this supplier. It then has a flexible PU bend limiter, which stops the cable bending or over bending, and then these what are called steel half shells, which basically act as ballast to maintain the cable's position on the seabed and stop it getting affected by the hydrodynamic forces offshore. Now, one of the key things that you see offshore is vortex-induced vibrations, and that can lead to damage to the cable. Obviously, you've got currents moving backwards and forwards, and this is supposed to stabilize it and stop that issue occurring. And that draws to a conclusion of the presentation. Hopefully just finished on time there, sorry, 3 minutes over. I hope you enjoyed it, and obviously I think we'll open the floor to questioning now.
Thanks very much, Ben. Very fascinating subject, and I'm sure there'll be quite a few questions. So my colleague Ian's going to manage the Q&A session. We'll take questions from the audience here at the waterfront and also on Zoom. So yeah, Ian.
Let's first of all have a question from the audience, if there is one. And then we'll move over to Zoom.
Okay, I'm wondering sort of when the thing is operating,
yeah,
you know, per meter or 100 meters, whatever you know, how much heat to get actually giving off?
Oh, okay, that's an easy one to answer. So an HVDC system is designed, its maximum operating temperature is 70 degrees C. So that's what it's designed for at the moment. An HVAC system can go up to 90 degrees operating. Now, its operating temperature is dependent on the generation assets, but its design temperature is HVDC 70 degrees, HVAC 90. The HVDC technology is now progressing more. Obviously, there's more AC systems at the moment. I think we're only the second wind farm, EA3 in the UK, using a DC system connection. And they're aiming to try and increase that operating temperature for the DC systems up to 80 degrees in the next couple of years.
Follow on that, then do you it's not your subject probably, but do you find sort of different marine life living around your cables because of the different temperature?
It really encourages marine growth. Yeah, it does. And you do see post installation, maybe 12, 24 months on, you see marine life growing there quite rapidly. Really cool ecosystems are developed. It only affects quite a small area of the seabed, and more often than not, the depth we bury the cable, there won't actually be any temperature differential at the seabed itself. You won't see a change there. But on the areas where we have the crossings where it's protected by a mattress or rock dump, obviously it radiates a bit more heat and you do see a lot of marine growth there.
Okay, we'll take a couple of questions off Zoom. We've had one from Kevin Field. Nothing lasts forever. How long do submarine cables last?
The design life of the submarine cable is 30 years. So we used to do 25 years, which is quite common in engineering design. We've now extended that to 30.
And another one from an anonymous person. As you mentioned, demand for offshore wind worldwide is increasing rapidly. Are you experiencing delays due to supply chain resources or vessel availability?
We're definitely seeing a constriction in the market. We're seeing a huge price hike in projects that we're looking to execute, and that is just down to supply and demand. So yes, we are seeing a constraint.
Do we want another question from the audience here? No? Well, there's some simple ones. While you're thinking, there's a simple one. I think he's missed the boat literally on this one. What's an RPL?
That's a route position list. So the RPL is a point every 1 kilometre on which your cable route is designed. So apologies for using acronyms and not explaining myself.
That's fine. Another one from anonymous. Regarding route engineering, do the conditions change over time, e.g. currents moving sands or soils? How does this affect your calculations with the cable design? Yeah,
it's a good point. So I suppose we always tend to design to the worst case scenario. So we have a lot of hindcast data. So on East Anglia 1, we have back to 1990 in wind and Met Ocean information. So we take the worst case design scenarios and add a margin on that, and that's what the cable is designed to. So yes, the conditions do change, especially with mobile sediments. You can have a 12-metre sand wave on your cable at one point, which obviously has a significant impact on the thermal performance. But then 2-3 weeks later, that cable may have moved across and you may have the trough of the sand wave and only have a couple of meters on top of it. So yeah, it does change, but we design for the worst case scenario.
If no one else has got a question, I've got one. Okay, talking about laying the cables in the route that you've prepared, you've dug your trench. Obviously, that takes some time. Before you lay the cable, there's a couple of questions. How do you ensure the cable goes in the trench, i.e. the position system?
I didn't touch on this one.
And the second one is, what stops all the tides filling up your trench before you've actually laid your cable?
In this instance, we use what's called a cable plough, which is probably a whole different lecture. The cable plough is, in East Anglia 1, for example, is a huge system, probably 50 tons in weight, and it's dragged behind the vessel, and the cable goes through the cable plough into the ploughshare, and it buries below the channel we've dredged out. So that's how you make sure. In a dredging scenario where the backfill, you basically do a calculation on the resedimentation. So you dredge your corridor to take into account the resedimentation between you dredging and then coming back to install. So it's an oceanographer's dream. Basically calculate the infill and make sure they dredge sufficiently to make sure that infill is taken into account for your final cable burial.
Thank you. Another one off Zoom. Do you think the long time frame for wind farm project is too long? And how does it compare to other countries?
I'd say yes, it is too long. I mean, it's been widely reported in the news that the process to achieve permission to build a wind farm is very long. As I said, we started EA3, EA1 back in 2011, 2012. So yeah, it is too long. Other countries have got the benefit of learning from our mistakes. So, you know, for example, the US new into the wind really. They still have quite a laborious consenting process as well. Bureaucracy, unfortunately, is a way of life, and there's so many stakeholders involved in what we do that unfortunately there's many hoops we have to jump through.
Okay, we've got plenty of questions coming up on Zoom. Before I move to some of those, one from the audience here.
It's not an engineering question, but it's related to what you were saying about the unexploded. What about wrecks? If you're looking at the North Sea, there's a lot.
There's a lot, yeah. So we avoid wrecks as much as we can. So in the broad survey we do at the very start of a project to get our cable route, a general cable route, part of that process is to identify any constraints in the seabed, wrecks being one of them. So archaeological constraints, we'd call them. Also, you obviously got wrecks, different wrecks. You could have a wrecked fishing vessel or a wrecked World War II vessel. Yeah. You then have a war grave scenario, which is, so a war grave scenario. There's also really cool instances where we've identified, I can't remember which one of our projects was, but we identified a submarine that had never been found before. And it was a lost submarine from one of the wars. And we found it. It's really cool to find one, but also a big issue. So yeah, we basically map the seabed for any known constraints that we've identified, and we avoid them as much as possible.
Okay, thanks. I'm not sure that you'll be able to answer this one quickly, but Alex asks, can you elaborate on the cable jointing process? Why does it take 7 to 10 days?
So let's talk about an AC cable. You've got 3 cores on an AC cable. Each core is maybe made up of 48 to 64 copper individual strands. So every single strand has to be joined together and tested. And once all the strands are tested, you then have to encase all the strands in a resin. The resin takes 24 hours to cure. So I'm not a jointing specialist. It's a very high level answer here, so apologies. But it's such a big cable. You're not talking about a cable you plug in at home. We're talking 300 mil cross section. So it's just physical size of it takes so long.
Okay. Any more from me? Yeah. No.
I'll ask one if I may. When the wind farm cables came into East Anglia, I mean, it came up near where I live, and I watched the drilling underneath the River Deben.
Yeah.
So there were like 3 tubes, 3 drills put through under the River Deben out the other side. Why have 3 cables? What's the purpose?
For the onshore route, so for the EA1 project, which you're talking about there, we have a trifoil cable, so 3 core cable.
Yes.
There's 2 of them offshore. So 6 cores in total. When they come offshore, they're bundled into 1 cable. So you've got a 3 core cable. You pull them into 1 HDD, and then they split out onshore, so that the thermal performance is increased, basically. You split the cables are split onshore into individual cores because it's easier to dissipate the heat that way for the East Anglia 1 cables.
Is that a DC?
No, that's AC.
It's AC.
For East Anglia 3, which is DC, they would have installed the same HDDs, but we've just got 2 conduits, 1 for each pole.
Right.
And then we've got a fibre optic one on top of it.
Okay, great.
So yeah, it's just really for the thermal performance.
Thank you.
One from, I don't know whether you'll be able to answer this one, Ben, but it's a more economic one. I've seen one graphic that says onshore wind power is cheaper overall than offshore, and another one that said offshore is cheaper overall. Can you compare total lifetime cost of onshore and offshore power? If it's not in your field.
I couldn't know, but there's a couple of points there. So number one, one onshore turbine would be maybe 1 megawatt. One offshore turbine is 15 megawatts. You pay about £1 million per megawatt for a turbine on its own without the installation costs. So yeah, onshore is cheaper, but your yield offshore is so much bigger. So the initial upfront costs for an offshore wind farm are huge. So EA3 is about 4 billion for a 1.2, 1.3 megawatt project. But the ultimate yield over the lifetime of the project, I think, will be significantly higher than it would be for an onshore project. And obviously it's a lot more windy offshore.
Yeah. Does maintenance play any part in that? You know, is it easier to maintain an onshore to an offshore?
Oh, definitely. Yeah. I mean, if you think we've got our operations and maintenance team that run out of Lowestoft, just to get to work, they've got what, an hour journey on the vessels just to get there. So yeah, maintenance a lot easier, I'm sure.
This is an interesting one that's come from Alex again. We know Russia is scouting our offshore wind farms. How long would it take to repair a severed cable?
So if you were ready to go and you didn't have to go through a prolongated procurement process, and you had a vessel ready to, you could, essentially repair a cable within a month. If you had everything ready to go.
Okay, thank you. Moving on. Are there design considerations made for the recovery of the cable after its useful life is ended, or is it, or if it's been damaged? Is it much the same but in reverse?
Yes. So by law, we have to have a decommissioning plan for the cables once they end their useful life, and it's very similar. A lot more agricultural. You basically get hold of the cable with a big clamp and try and rip it out the seabed. That's the long and short bit. But there also has to be an ecological assessment to see if it actually is better to leave it in place. Obviously, it's already buried. As long as it's not exposed, there's an argument that you probably do more harm than good actually physically taking it out.
Any more from here? In that case, we'll have a couple more, and then I think we'll have to call it a day. And I'm sorry for the people that have asked questions, but we've got so many questions here, we're not just going to get through them all. But related to the Russia one, any planning for defence or repair against enemy cable destruction? A threatening ship made the news recently.
Yeah, that's way out of my wheelhouse. The only thing I would say is we try and bury the cables over 1 meter deep. We can't defend them against Russian sabotage, unfortunately.
Another one which we might just make this the end one, Kevin. Do you
Yes,
think?
sure, yes.
Is the full offshore length of the cable protected from anchors?
Yes, yeah. So we aim to bury it about 1 meter below the stable seabed to avoid anchors. So on East Anglia 3, a minimum burial depth of 0.5 meters will protect you from all fishing activities. And I think 70% of anchor strikes that could occur in that area. So yeah, always protect the cable.
Right, I think probably we need to leave it there.
Great. Well, thanks very much, Ben. Great presentation.
Thank you.
Very, very interesting subject. And Ed, thanks very much for coming along, and both of you, for Scottish Power for providing a very interesting talk. Please can we thank them in the usual way.
Thank you.
Right, I'll just do a plug for our forthcoming events. Just bear with me. I'd like to go through just to highlight some of the future events that are coming up. Got 3 that I'd like to highlight. The first one is the routes to registration. That's going to be on the 7th of June. That's a webinar. So for those who are thinking about professional registration, technician, engineer, chartered engineer, etc., career progression through the IET and professional registration, that will be a good webinar to view. We've also got a visit to Bawdsey Radar Museum. That's on the 21st of June. That's obviously a face-to-face meeting and visit. Fascinating subject, radar. fascinating place, Bordsey, where radar was pioneered many years ago. So Graham Murchie, who's a trustee at the Bordsey Radar Museum, is kindly going to give us a talk on the 21st. And then on the 18th of July, we've got a talk entitled Getting Off Gas. That's going to be at the Atrium, University of Suffolk, by Dr. Phil Wallace, and that's going to be a hybrid event as well. So the first one is pure routes to registration, which is a webinar. The second one, Bordsey Radar Visit, face-to-face, and the third one is a hybrid event, Getting Off Gas. All the details of those events are on our IET NGEX community site page. Link is in the slides, and CPD certificates for today's presentation and all previous Angling Coastal Local Network talks are posted on that site. So once again, I'd like to thank my colleague Ian for the Q&A session, Julie and the IET HQ staff for setting up the webinar. And finally, again, a big vote of thanks to Ben for pulling together a fascinating talk. So thank you very much.